All right, so welcome to another exciting episode of AP Chemistry here at Spain Park High School. Today is Thursday, September the 25th. And what are they supposed to do, Jonathan?
Hit that like, smash that subscribe button, and ring that bell.
There you go. Now you know what to do. All right, so today we're going to start talking about how we measure the concentration of solutions. We just finished up talking all about the solution process. How do things dissolve? Okay. Now we want to go with the more quantitative ideas of, well, how do I know how much is in there? So if I just take some sugar, and I just scoop some sugar into here, and then I put some water into it, is there any way for me to know, even when it dissolves completely, okay, so I can just stir this up, okay? May have to add a little more water, we'll see, okay? But let's just even say assumes that it all dissolved, or maybe even some of it didn't dissolve. Is there a way for me to know anything now quantitatively as far as how much sugar is in here?
Not for real.
Not for real, okay? Even if I measured 5 grams of sugar and then just dumped a whole bunch of water in there, unless I used the entire solution, I wouldn't know how much sugar I'm using. So we want to be able to come up with some kind of way to measure the concentration. Concentration is nothing more than a ratio between how much solute do you have versus how much solvent or how much solute is in a given amount of solution. Molarity is by far the most common measure of concentration. It is by far the most useful measure of concentration. There are 3 others that we will look at super briefly. Molarity, and you don't need to write these down, I'll go through them later. Okay, but it's going to be molarity, which you did in Chemistry 1 when we did the freezing point depression and we did ice cream lab. You remember when you did the ice cream lab? You had to measure the molality of the solution, not the molarity of it. But the reality is the only time I ever know that you use molality is in those freezing point, boiling point elevation problems. And AP has decided that freezing point and boiling point colligative properties has already been covered in Chemistry 1, so we don't need to cover it in AP, so it's not even included in the AP curriculum. So we're never going to do a freezing point depression, boiling point elevation, or ice cream lab. Oh. Okay.
I missed ice cream lab.
Another way is you may have heard of measurements in parts per million. Okay, that's kind of a percent. Percent is parts per 100, and then parts per million is parts per million. That's the name. Nowadays, the measuring devices have gotten so good that we can do parts per billion and even parts per trillion, meaning just very, very super dilute, but we can still measure it. And we'll look at how to measure those. And then we have this thing called mole fraction, and we do need to know how to do mole fraction. And what you don't have to be able to do is convert between the 4, okay? However, in college you do. So we'll go through and I'll spend 15, 20 minutes or so, maybe one set of practice problems, going through and how do we convert between molarity, molality, percent, and mole fraction, and then it'll be bonus on the test, okay? Because it's not on the AP, but you do need to know it for college. So I'm not going to spend a lot of time talking about it, but if you want to spend the time kind of learning it and working through the problems, then I'll put it on as a bonus problem for that. So we're really going to focus in on molarity because that's the one that we're going to use all the time. We use that in stoichiometry as well. So molarity, okay, is simply a ratio of moles of solute over the volume of solution in liters. So liters of solution. So we can say it's going to be moles per liter, okay? Now, we're never going to go measure out moles. What are we going to measure out in a lab?
Grams.
But how do we change grams to moles?
Molar mass.
So the more useful form is grams over molar mass over liters. is gonna equal, and we can just go this other way, over is equal to molarity. And molarity is a capital italicized M. Now can't write italicized. I can't do an italicized when I just write it, so it's just gonna be a capital M. But when it's ever on a keyboard and you type it in and you see it, it's gonna be an italicized capital M. It's gonna always, so you're always gonna translate this capital M. So if we said something was 3.0 M NaOH, that means it's gonna be a 3 molar NaOH solution. That means there's gonna be 3 moles for every liter of solution. Okay, so the capital M is always gonna translate to these units. Okay, so in terms of trying to make units cancel out, when you go and put it into the stoichiometry, you want to set the units up so they cancel, you're going to want to put it in like this, not like that. Okay, so molarity is always moles per liter. Now, a solution by definition is a homogeneous mixture. What does that mean? Same throughout. So if I have, this says that it's 3 moles of NaOH for every 1 liter of solution. And that's my abbreviation for solution. It's not 1 liter of water, it's 1 liter of solution. Okay? So what if I have and that's 1,000 milliliters. So what if I have 500 milliliters? How many moles of NaOH am I going to have? 1.5. 1.5, because I have half a liter. Since it's homogeneous, it's even throughout. Okay, it's not like all the NaOH is on the bottom or anything. Since it's even throughout, if I have a half a liter, I'm going to have 1.5 moles. If I had 100 milliliters, I'm going to have 0.3 moles. Because I have a tenth of a liter, I'm going to have a tenth of whatever my molarity is. So it gives me, so however much I have, okay, come on. Just give my handful if you want. Okay, we can have food as long as it's not a distraction. Right? We can have food as long as it's not a distraction. Okay? Now, so we've learned, and we've already learned this, and we're relearning it again, reviewing it, that the molarity times volume always equals moles of solute. Moles per liter times liters equals moles. Right? So what is moles per liter going to be a conversion factor between? Moles and liters. Moles and liters. So now if we have a solution volume, 50 milliliters of NaOH, and I know the molarity of it, I can use the molarity times my 50 milliliters, or my 0.05 liters, and I can know exactly how many moles are in my solution.
So basically reconstructing that problem.
Yeah. So the molarity just gives us a ratio of how much solute there is in a given amount of solution. It's the most common, so I can just go measure out, and that's what we did in our lab. We measured out, 8 milliliters of the iron chloride, but we were told that was grams per liter, so we knew exactly how many grams, thus how many moles. If we used in the Penny lab, technically we used 50 milliliters of 6 molar NaOH. So how many moles was that?
6.0 equals.
Okay, how many moles of NaOH were present? How many moles of NaOH did we actually have in our flask? Well, how would I do that?
You do 6.0, that's done.
Okay, well, I can just plug it in. Okay, I know this is how I really want to do it. I'm going to start, and I'm going to know that this is really 6.0 moles per liter. This is going to be how many liters? 0.0500 liters. So always start with the simplest unit, 0.0500 liters times 6 moles over 1 liter. So I'm going to end up having 6 times 0.05. What's that come out to? Mental math. 0.3. So I know that I use 0.3 moles of NaOH in my penny lab. Now, when I went and made, okay, so here's the other question. All my markers are drying out.
You gonna shoot one?
No, not yet. Just gotta keep grabbing new ones. So when I went and I needed to make this, getting ready for the lab, I gotta do this anytime we have a lab. So I know we needed 6 molar NaOH. So I said, okay, we got 20 groups. Each group is gonna use about 50 milliliters. So I need 2 liters of 6 molar NaOH. Okay? So what do I need to do? Well, I need 2 liters of 6 molar NaOH. How do I make that? Well, molarity is equal to grams over molar mass over liters. Right? So I know that I want I need it to be 6 molar, and we can even go 6 moles per liter, is equal to, the question is how many grams do I need to measure out, divided by the molar mass of NaOH. 16 plus 1 is 17 plus 23, it's 40 grams. Divided by, I need 2 liters of it. So how do I solve for G?
Multiplies by 80.
Okay, well that's combining 2 steps. So the first thing you're going to want to do,
Multiply by 2.
multiply by 2. So you're going to get 6 moles per every 1 liter times 2 liters. Now technically we could have started with 2 liters. Okay, that gives me how many moles I have. Molarity times volume equals moles. Then how do I get to grams? Multiply by the 40 grams over 1 mole. Moles cancel here. So I'm going to have 80 times 6. 480 grams of NaOH. Okay, so I had to go and get 480 grams of NaOH, comes as a solid, weigh it out, and then dissolve it in enough water to make 2 liters of solution. Okay, so I mean, it's really based upon a molarity. If you have this formula right here, you got 4 variables. That's not really a variable, the molar mass, because you're going to know pretty much, if you know the formula of what you're looking for, you know the molar mass. Okay, so we can be looking for all the different factors here. Most of the time, you're either looking for the molarity of the solution, or you're looking for how many grams do you need to make a particular solution with a given molarity. Okay, so it's generally one of these 2 that you're looking for. So how do we then actually make the solution? What's the proper technique? Okay, what's the proper technique? Okay, if we want to make a solution, now this is important because they do ask this question for you to be able to write it out as a free response question. Okay? Please tell me, please tell me, please tell me, yes. Okay? To create a solution of a known molarity, so let's just say this time we want to make 250 milliliters of a solution of known molarity. We're going to use a volumetric flask. Okay? A volumetric flask What does the name tell you it does?
Just volume.
Okay, a whole bunch of volumes?
No, metric.
Okay, it's a measured volume. It's only going to be, if it's a 250 milliliter volumetric flask, it's only going to measure 250. It's got one line on it right here. Okay, everybody see the one line on the neck? Okay, it's right there. Okay, y'all see that? So you fill this up to this line right here, bottom of the meniscus on the top of the line, and they make the neck skinny, so you know it makes it easier. When it's real wide, then it's not as accurate. The skinnier the neck, the more accurate it's going to be on there. Okay, so does everybody see that there's one line right here on the neck? So you would fill this up to where the bottom of the meniscus is on the top of that line. So then I would know, notice again, and this is real important, you measure out your mass, okay? And I personally would probably try to measure it directly into the volumetric flask. Sometimes what I do is, because it's hard to get it down into here, I'll measure it into, I know I need 250 milliliters. So I might measure it into a bigger beaker, but only use 200 milliliters of water and dissolve it in 200 milliliters of water. But ideally what you're going to do is you're going to add your mass. So I would go, now I'm not going to need that. I'm going to need, 4 times less than that, and 250, actually 8 times less than that. So I'd only need 60 grams of NaOH to make 250 milliliters of it. So I'd get my 60 grams into here. Then you're going to add enough distilled water to go about 2/3. You don't want to fill it all the way up. Anybody want to think about the practicality of why I don't want to fill it all the way up to start with? What has to happen to that solid? It's got to dissolve. Okay? If it's filled up to the top, it's hard to shake it. So if you fill it like 2/3, then you can just swirl it and get it to dissolve. Okay? So you fill it about 2/3 full, then just swirl, get it all to dissolve. Then, using a squirt bottle, being very careful, you fill it up the rest of the way to where the bottom of the meniscus is on the top of the line. Then we can put a cap over it and then just mix it 1 or 2 times to get it evenly mixed all the way through. Because if you don't mix it again, then you're just going to have more water on the top than you are. But if you just kind of, you have a cap that you can put over this, and you just cap it up, turn it upside down a couple times, then it mixes thoroughly. Okay? So, weigh it out, put the copper sulfate into the flask, add water and swirl, and then add water until it gets to the line. We got to know those steps. Okay? Now notice you're not adding 250 milliliters of water. You're adding enough water to get to 250 milliliters because the solute is going to take up just a little bit of space. Okay? So if you went and added 250 milliliters of water, it may go above the line. Sometimes, it's kind of crazy, alcohol in water, if you mix 50 and 50 and you put it in, it only goes to 95. There's enough room and they're so attracted to one another, they actually can fit in between each other and take up less space. So you're always going to add enough water. I know it's kind of crazy. Okay?
Can you get like a visual?
How does that make sense?
Yeah, we can.
It's because because the molecules are moving, there's space in between, and especially with the ethanol molecules, they're bigger. There's space in between, and they just fit into those spaces and take up, so they don't take up the full space.
I'm saying that's cap.
Okay.
I'm saying that's cat. That doesn't make any sense, Mr.
Okay.
Roberts. You're putting in 50, you're putting in more 50, and then you end up at 95.
Science doesn't always make sense. It just is. It's like magic.
Cap.
Okay? We'll see. Now, so we add enough water, okay, to get to 250. Now, it's important on those words. Now, I stressed on the last free response when we're going over the test. Words are important, okay? You got to say it the right way. You don't add 250 milliliters of water. You add enough water to get 250 milliliters of solution. You add water to get to the 250 line. Okay? So when you're answering this, I mean, you're going to weigh out the solid. You're going to put it into the flat. You always want to use a volumetric flask. You will not want to use a beaker. You will not want to use an Erlenmeyer flask. You want to use a volumetric. This is much more accurate. Beakers are the least accurate way to measure volume. They're only plus or minus 5%. Plus, it's wide, and so you can't even see where the meniscus is going to be right on that line. And so the more narrow the neck, the more accurate. So we're going to use, we all used a burette last year in doing titrations. A burette is the best way to deliver if you need to deliver random volumes. Because you can measure 5 milliliters, 10 milliliters, 12 milliliters, 12.5. A volumetric flask only delivers one volume, a measured volume. But it's the best way to make a solution. You're always going to want to do this. So we're going to have 2 labs. Number one, we're going to do one that's more of a stoichiometry. It's going to be a percent. We're going to have a mixture of NaCl and NaNO3. And your job is going to be figure out what percent of the mixture is NaCl by doing a titration with silver nitrate. Okay? And you're going to titrate it until an endpoint. Okay? And then we're going to do one where we make solutions of different concentration. It's called Beer's Law, and we're going to be able to then use a spectrophotometer using light passing through the solution. And the darker the solution, the less light that passes through, and we can tell the concentration based upon how much light passes through the solution. That's what a spectrophotometer measures. And we're going to do those 2 labs. Okay? So this is super important. So this is kind of when we do the Beer's Law, we're going to practice making the solutions. We're going to make a stock solution. Okay, what we start with, like our 6 molar, and then we're going to dilute it down into 4 other solutions. So how do we dilute? Glad you asked. Okay? When you have a dilution problem, how do you dilute something? If you dilute something, do you make it more concentrated or less concentrated?
Probably like less concentrated.
Less concentrated, right? So how do you dilute something? Add water. Okay? You're just going to add water. You dilute it. So if you're always going to start with a stock solution, something concentrated, stock solution is your starting material. It's always going to be the most concentrated because you're not going to be able to make it more concentrated. You're just going to be able to add water and make it less concentrated. Well, it's a super easy equation where we take the molarity of the concentrated times the volume of the concentrated is equal to the molarity of the dilute times the volume of the dilute. So C stands for concentrated, D stands for dilute, and it says it right there. So I also had to make 6 molar H2SO4. Okay? How to make 3 liters of 6 molar H2SO4 from concentrated H2SO4, which is 18 molar. So right there is my H2SO4 in that jug right there, the yellow cap. That's 18 molar, 95% H2SO4, 5% water. So it's almost pure H2SO4. So what is the molarity of my concentrated? What's the molarity of the concentrated? Okay, wait, let's just read this. Read the question. How to make 3 liters of 6 molar from concentrated that's 18 molar. Which is more concentrated, 18 or 6? 18. Okay? Don't make that complicated. Okay? 18 molar is more concentrated than 6. So my 18 molar is the concentrated, the 6 molar is the dilute. Right? So I'm just going to plug in. The molarity of my concentrated is 18 molar. The question is how much of it, what volume of the concentrated do I need, okay, to make 3 liters of 6 molar? The molarity of the dilute times the volume of the dilute. Okay? So all I gotta do is divide by 18, right? So 6 molar, 6 divided by 18 is a third. So I need 1 liter. So I need, the volume of the concentrated is equal to 1 liter of 18 molar H2SO4. And then what do I do? What do? So I measure out 1 liter of 18 molar. I take that, measure out a liter of it. So how do I go from 1 liter to 3 liters? I'm in the lab. How do I make this? I just figured this out.
And 3 times as much.
What total volume do I want? 3. So I have 1 liter. How do I make it go to 3 liters? Add water, right? That's how you dilute something, is you add water. So I have to go and I measure out a liter of the H2SO4, and then I need to add enough water to it all until it gets to 3 liters. Now the reality is I don't have a 3 liter container that I can just measure. Okay, so I'll probably do this 3 times. So if I went to 1 liter, that's going to be 0.333 liters, or 333 milliliters. So I'll measure out 333 milliliters and then just add water until I get to a liter. Now the reality is with acid, remember what I said? Do we ever add the water to the acid?
No.
Okay, so this one here, this is just a lab safety. Always add acid to water to dissipate the heat. Dissipate the heat. When I add sulfuric acid to water, it gets extremely hot, so hot that the water almost boils. I can't grab the graduated cylinder for a while after it's so hot. Okay? If you add a little bit of water to a lot of acid, that water immediately boils, gets so hot it just boils and it flashes out and it brings hot, boiling acid water out on you. It's not good. Okay? So what you have to do on this to dissipate the heat, I know that I'm going to dilute it to a liter. I'm going to use 333 milliliters. So that means I can go up to 666. But what I'm going to do is I'm going to put in about 500 milliliters of water. Then I'm going to slowly add in my 333 milliliters of my acid. And then I'll fill it up with water the rest of the way. Because you want to have as much water present to dissipate the heat so the water doesn't boil. You always add acid to water. That is a type of question, that's a safety lab question that can be asked on my test, the AP test. So whatever it takes to highlight that, to underline that, to bold that, okay, that's super important. Lab technique right there. I have to make sure I follow that all the time. You know, I have a lousy, I pay the price on my hands for lousy lab technique, but I don't mess with that. They're getting there. This finger now, I can use my fingerprint on this one again. This one I can't use the fingerprint yet. It's still like there's a little flake of skin coming off. It's still pretty dry. It's still kind of a little tender. Okay. All right. So when we do a dilution problem, first off, you look for the word dilute. Or you're going from something concentrated to make something less concentrated. Molarity of the concentrated times the volume of the concentrated equals molarity of the dilute times the volume of the dilute. Super easy. Okay? So let's see. Break open the new books. I didn't plan ahead and pick up the problems.
Like, this job, you were saying just like regular tasks, no charge. Like, when it's like, we should get that.
You might want to explain it just to be still.
Just like, Yes.
unionized and then put in water.
So potassium would explode and then into the water without a charge.
I'm not listening to you at all. All right. Right now, on page 157 in your textbook, 5-7. And by the, I looked up, by the way, what 6-7 means in the Urban Dictionary.
What did it say?
It says that just simply means like so-so, indecisive.
Yes.
Okay? And that's, and y'all, this hand motion's been around forever. This hand motion means 6 to one hand, half a dozen to the other. How much is a half a dozen?
6.
So if you put 6 in one hand and you put a half a dozen in the other, it's like 6.
26.
Okay? 6. It's like the same thing. It's like it doesn't matter. It's like so-so. It's like indifference. It doesn't matter. Okay? So yeah. Okay? Just don't go 666. Okay? Because we all know what that one is. Yeah, devil. Okay. Do you remember my Vices of This World demo with the nitric acid where the black grew out of the beakers and the black
Isn't there right there?
Yeah. I'll do that too. That's the one I'm gonna do. But anyway,
Yes.
It like,
yeah.
it like shoots out.
So it doesn't shoot out, just kind of grows.
Grows out, yeah.
But anyway, so I'm doing that today, and so of course, Dr. Esslinger chose to come in and observe that one. As no, I did it.
Oh, yeah, you're cooked.
Yeah.
He's cooked.
Wait, what?
He's talking about like, he's talking about the devil and Jesus.
Yeah, I saw the Vices of This World. Anyway, I was challenged on whether I should just say go for it or not.
She can't fire you.
All right. If she does, she does. Okay, page 157. Right now, just in your notes, 61, 63, and 73. 61, 63, and 73. Page 157.
61.
Mr. Rob.
Okay, just to see if you can do this, and go ahead and hit pause.